All right, welcome. So today we're going to tackle a concept that you see in health news all the time, but honestly, it can be a little tricky to wrap your head around. We're talking about the odds ratio. But stick with me, because by the end of this, you'll see it's not some confusing statistic. It's actually a brilliant tool researchers use to solve a really big puzzle. You've seen the headlines 100 times, right? Daily coffee linked to lower risk of X, or new medication associated with side effect Y. But have you ever stopped to wonder, how do they actually measure that link? How do they put a number on it to say how strong that connection is? Well, that is a fundamental question in the world of epidemiology. So, before we can jump into the odds ratio, which, spoiler alert, is a really clever workaround, we first have to understand the most direct, most intuitive way to measure these things. And that, my friends, is the gold standard. It's called relative risk. Relative risk is pretty much exactly what it sounds like. It's just a simple, straightforward comparison. You take the risk of getting a disease in one group, say people who are exposed to something, and you just divide it by the risk of getting that same disease in a group of people who are not exposed. That's it, a direct ratio of two risks. Now, to get those risk numbers in the first place, you need a very specific kind of study. It's called a cohort study, and this is the classic forward-looking approach. You find one group that's exposed to something, another group that isn't, and then you wait. You follow both groups forward through time to see who eventually develops the disease. Okay, let's make this real with an example. Here's some data from a hypothetical study looking at smoking and heart disease. So researchers followed 3,000 smokers and 5,000 non-smokers. At the end of it all, they just tally up the results. For the smokers, you see 84 out of 3,000 got heart disease. That gives them an incidence or risk of 28 per 1,000 people. For the non-smokers, it was 87 out of 5,000, which works out to an incidence of 17.4 per 1,000. And now for the easy part. To get our answer, we just divide the incidence in the smokers by the incidence in the non-smokers. So, 28 divided by 17.4, and that gives us 1.61. What does that mean? It means in this study, smokers had 1.61 times the risk of developing heart disease compared to non-smokers. See? It's a really clear, direct, and easy to understand result. Okay, but here's the massive problem with that. What if the disease you're studying is incredibly rare? I mean, you'd have to follow millions of people just to find a handful of cases? Or what if it takes decades, like 50 years for some cancers, to even show up? A cohort study would be, well, astronomically expensive and take a whole lifetime to finish. It's just not practical. So researchers needed another way. So, how did they solve this problem? Well, this is where things get really clever. Epidemiologists basically flipped the whole research question on its head with a totally different study design, one that's way faster and much more efficient. It's called a case control study, and instead of starting with who's exposed and waiting for the disease, you start with the disease itself. So first, you find a group of people who already have the disease. Those are your cases. Then you find a similar group of people who don't have the disease, and those are your controls. And here's the absolute key difference. Once you have your cases and your controls, you don't look forward, you look backward. You basically play detective. You interview them, you check their records, and you figure out what they were exposed to in the past. It's a total reversal of how a cohort study works. But this creates a whole new puzzle. Because we started by hand-picking sick and healthy people, we have no idea what the total population of, say, smokers or non-smokers was to begin with. And that means we can't calculate those incidence rates, the very building blocks we needed for relative risk. It feels like we've hit a statistical dead end. So what do? They can't calculate risk. But it turns out they can calculate something else that works as a fantastic substitute. Instead of comparing risks, they compare odds. And this brings us to the hero of our story, the odds ratio. Okay, first a super quick clarification. Risk and odds, they're related, but they're not the same thing. Risk, or probability, is the chance of something happening out of all the total possibilities. Odds, on the other hand, are the chance of it happening compared to the chance of it not happening. So for example, if there's a 1 in 5 chance of rain, the risk is 20%, the odds are 1 to 4. Okay, with that in mind, let's see how this works. This right here is the classic 2x2 table that you use to organize all the data from a case control study. Pretty simple, right? A is the number of cases who were exposed, B is the controls who were exposed, C is cases who were not exposed, and D is controls who were not exposed. So this is where the logic totally shifts. Instead of looking at the risk of getting the disease, we're now looking at the odds of having been exposed in the past. So first, we look only at the cases, the sick people, and we ask, what were the odds that they were exposed? That's just A divided by C. Then, we do the exact same thing for the controls, the healthy people. What were the odds that they were exposed? That's B divided by D. And the odds ratio is simply the ratio of those two odds. You take the odds of exposure in the cases, and you divide it by the odds of exposure in the controls. Now, the formula simplifies really nicely to what we call the cross-product ratio, just A times D divided by B times C. And that one number gives us a really powerful measure of how strong the association is. So we have this number, the odds ratio. But why does it matter so much? And how does it connect back to that gold standard, the relative risk that we started with? So here's where we can see them side by side. Relative risk is a direct measure of, well, risk. It's perfect for cohort studies. The odds ratio is a measure of association, and it's the workhorse for case control studies. But here's the really cool part, the magic link between them. When a disease is rare, which is exactly when we need to use these case control studies, the odds ratio turns out to be a remarkably good estimate of the relative risk. For all practical purposes, they basically become the same thing. So what's the bottom line? The odds ratio is really the key that unlocks the power of the case control study. It lets us measure the strength of an association even when we can't calculate risk directly. And for all those rare diseases where case control studies are so vital, it gives us a fantastic estimate of the true relative risk. It allows scientists to investigate links that would otherwise be almost impossible to study. But of course, finding a strong association is just the first step, right? An odds ratio of, say, 3.0 doesn't automatically mean the exposure caused the disease. What about other factors? What about just plain old coincidence? Well, that leads to a whole new set of fascinating questions about things like confounding, bias, and what it really takes to prove causality. But that is a topic for another day. Thanks for joining me.